Welcome back, everybody. Today we're going to tackle lesson 5.3, okay, a short lesson looking at connecting functions with their first and second derivatives. Now, a nice thing about this lesson is technically it's not any new information, as we've been looking at how we can determine mins and maxes using our first derivative or concavity using our second derivative. There's some connections between those different functions. What we're going to do this lesson is try to lay them out explicitly for you and just make sure we're okay with all those connections. So here we go with that. All right, we're going to start off with a graphing question. Okay, it says sketch a graph of the function f of x given below. So this polynomial here, and include proper intercepts, extrema, as in mins and maxes, and points of inflection. Okay, now AP exam time, you're not going to get asked to graph an entire function from scratch. You'll be asked things about the function like what are its maximum values or where is it concave down. Okay, but probably not going to get asked to put it all together. I do want to start off by putting everything together here just to make some connections between the graphing that you learned how to do in pre-calc that we've been using as we've gone through the semester, okay, and then also the first and second derivative stuff we've been doing in our last few lessons. Okay, so let's start off with the intercepts part. Okay, where does this graph hit the x-axis and y-axis? Now, no calc involved for that. That's just pre-calculus information. For the x-intercepts, what we can do is just take this function and set it equal to 0. Okay, that's going to be where we hit our y equals 0, the x-axis. Looks like this guy will factor. We can pull an x out. Oops, I'm supposed to throw the 0 there. And then looks like this quadratical factor as an x minus 3 times x minus 3. All right, so for that, I know I'm going to have x-intercepts at x equals 0 for this term of x, factor of x, sorry. And then also an x equals a positive 3 from these two factors of x minus 3. We won't get into the bouncing multiplicity part. We'll kind of let the calc take care of that for us here. And just kind of move on from the x-intercepts. All right, now a reminder, I could also find the y-intercept by going f of 0. Okay, because along the y-axis, our x-axis is going to be 0. Now we can already tell what that is 0 here. I'd get the same thing if I plug things in. Everything's 0. Okay, but if I had something else, that'd be how I could figure that out. All right, last thing I could do, I suppose, from back in pre-calc is talk about my end behavior. Is this graph starting on the coming from up or down and finishing up or down? Remember, for that, what we'll do is we'll look at the first term, the term with the highest degree, and think about what happens when I plug negatives into that. Well, negative values to the third would be negative, which is why my graph's going to start down. And then positive values to the third would be positive, which is why I know it's going to finish going up like this. All right, so we've got our intercepts and end behavior, and that's really where we stopped it in pre-calc last year. Let's get into the actual calculus here then, and look at finding the extreme and the inflection points. So kind of start things fresh here. All right, for the extrema, the mins and maxes, what we'll do is we'll look at the derivative of my function. We'll find f prime of x, and using my power rule, that's just going to be a 3x squared minus a 2 times 6 is 12x plus 9. And we'll set that equal to 0. And I suppose we can factor once again. I can pull the 3 out of all these terms. Looks like this will factor as an x minus 3 times an x minus 1. Okay, so we can find the zeros of that first derivative of x equals 3 and x equals 1. Okay, we said these were our critical values. And as far as determining whether they're mins or maxes or neither, what we did is we looked at the first derivative test. That's where we looked at a sign chart of our derivatives. We know we're going to have zeros at, like we said, a 1 and a 3. We want to decide what the signs are on these different intervals between those zeros. Okay, we could plot points, or we could just use the fact that we know this is a positive quadratic. I know it's going to look something like this. Okay, so our derivative will be positive to the left of 1 and to the right of 3, and negative in the middle. All right, so we know we're going to have then is a maximum value at x equals 1, okay, because my graph's going to go from increasing to decreasing when that first derivative goes from positive to negative. Okay, so it'll be going up and then switch down. And I can find that actual value by going f of 1. Okay, going back to the original function here, that'll be 1 to the third minus 6 times 1 squared plus a 9 times 1. Okay, so in other words, 1 minus 6, which would be a negative 5, plus 9 to be a positive 4, equals 4. Okay, so I know I'm going to have a max at 1, 4. We can go ahead and plot that. Oops. And then by the same reasoning, we know we're going to have a minimum at x equals 3. Because my derivative switches from negative to positive, my graph is going from decreasing to increasing. And that y value is going to be f of 3, which would just be a 3 to the third minus 6 times 3 squared plus 9 times 3. I could do a little arithmetic in my brain here, or I can recognize that I already have the 3 right here. We know it's going to be a 0. All right, so that'll be my minimum value here. All right, so we've got our intercepts, our max, and our min. We could just connect the dots from here, but I also want to come up with the points of inflection. So let's go ahead and get into our second derivative then. I suppose we'll leave our first derivative there. Okay, f double prime of x will be equal to a 6x minus 12. Okay, to find points of inflection, we'll set that equal to 0. So in other words, 6x equals 12, and x is equal to a 2. Now, is that a point of inflection? Well, let's look at our sign chart. We've got the 2 here. Does it switch signs on both sides of these? Well, I'd say yeah. If I plug in a 1, for example, I'd have 6 minus 12, which would be a negative 6. That would be negative. And if I plug in a 3, I'd have a 18 minus 12, which would be a positive 6, something positive. Yep, so we are changing signs. We are changing concavity, all right, at that point, x equals 2, which is why I do know I have a point of inflection. Or we'll just say inflection point. At x equals 2. And then again, we'll figure out what f of 2 is so we know where to actually plot that point. So for the y value, we'll plug that 2 back into the original function. So 2 to the third minus 6 times 2 squared plus 9 times 2. So 8 minus 24 is going to be a 16, negative 16, sorry. Plus an 18 will be a 2. Okay, so now I have an inflection point at 2, 2. All right, so there's all the different points we can plot, and then from there we can just connect the dots. Bear with me here, and this is tricky to do on a computer screen. And my graph would look something like that. Okay, including again the zeros coming from the zeros of my function, mins and maxes coming from the critical points, the zeros of my derivative, and then that point of inflection where we flip from concave, in this case, down to concave up at the zeros of my second derivative. All right, so there's basically everything we were working on the last couple lessons, all laid out in one example there. All right, next thing we're going to do is think more in general terms. Okay, how do the graphs of f, f prime, and f double prime, the function, its first derivative and second derivative, relate to each other? And to do that, as an example, I've got a function f of x along with its first derivative and second derivative, and a few different specific x values that we can match up between these curves. And in your notes, what you have is a table to fill in where we want to talk about when f is doing something, such as increasing, what do we know about f prime and what do we know about f double prime? Okay, so let's start off with that. When f of x is increasing, okay, so as in this function, when I'm going up as I move from left to right, what is my f prime doing? Okay, well, when our function's going up, that means that its derivative, the slope of its tangent line, is going to be positive. And we see that on this graph here, where our first derivative is above 0 between those values of a and b. Okay, f of x is increasing from a to b. Our first derivative is above 0 from a to b. So that's where we can just say f prime is positive when f of x is increasing. Now on the flip side of that, when f of x is decreasing, so as when it's going down from left to right, which we see on this function in green here, moving up to a, and then also from after x equals b, our derivative is going to be negative because the slope of those tangent lines are negative. That corresponds with this part of the graph here. All right, so something we've been looking at for a few chapters now. When a function is increasing, that's when its derivative is positive. When it's decreasing, its derivative is negative. Now, as far as what's happening with my second derivative, these two kind of spaces on our table, I'm going to leave blank. Okay, there's not going to be something specific that a second derivative is doing when f is increasing or decreasing. Notice here we've got both positive and negative values over both those intervals. Okay, so that'll be something we leave blank here. All right, next up, let's talk about what happens at local maximums and local minimums. So when f of x has a local maximum, as in at x equals b here, with this function, what's happening at b on our derivative? Okay, well, the function, when it switches from increasing to decreasing, that's when we're going to have the maximum. As far as the derivative goes, that's when it's going to switch from positive to negative. And that was essentially our first derivative test. Okay, we looked at where our first derivative was equal to 0 and whether it was switching or not. And same idea here, if I have a minimum, that's where my function is going to go from decreasing to increasing. So my derivative at that point will be switching from negative to positive. All right. Now this one we can actually get into our second derivative, starting off again when f of x has a local maximum. Now remember, when we have a local maximum, that's when our function is going to be concave down. This is an example of a concave down function, opening down. And we know that when our function's concave down, that's when that second derivative is going to be negative. So in other words, when we have a local maximum, f double prime of x is going to be negative. Same idea then, our minimums are going to occur when our function is concave up, okay, opening to the up, and that'll occur when our second derivative is positive. Now, speaking of concavity, let's talk about what's happening when our functions are concave up and concave down. Okay, first up, concave up. Where is my original function concave up? We just traced it a second ago. That's going to be up until the green portion here. Should probably shade that a little bit better. And we already said that's going to happen when our derivative is positive. When our second derivative is positive. Now then next we'll get into what is happening with our first derivative when our function's concave up. Well, if the second derivative is positive and the second derivative is the derivative of the first derivative, that means the function has to be increasing, which is true in this case up until we switch concavity at c. Okay, so when our function is concave up, the first derivative is going to be increasing. As an example, we looked at tangent lines, for example. If I start making some tangent lines on this graph, they're negative, but they're becoming less negative. That slope is increasing as we go. And by the same token, when my function is concave down, like we see in blue here, my second derivative is going to be negative. And if a derivative of a derivative is negative, that means that that first derivative is decreasing. And then last thing, let's talk about when our function has an inflection point. Okay, so as in a point where we flip from concave up to concave down, or vice versa. Okay, what's happening with, again, with our concavity inflection points? We'll think of the second derivative first. What's happening with our second derivative? Okay, well that's going to be where it's switching signs. Okay, and if we had specific names for inflection points when we're going from up to down or down to up, we could say more about specifically how it's switching signs. But if it switches from either positive to negative or negative to positive, we know we'll have an inflection point. Okay, now then back to the first derivative, what's happening at x equals c? Well, here notice we have a maximum, which makes sense where our function is switching from increasing to decreasing. Whoops. Okay, so that's where we can say that our first derivative has a min or a max, okay, depending on whether we're switching from concave up to down or down to up. All right, so again, there's all the relationships we've been talking about for the last couple of lessons, just laid out for you explicitly. Hopefully that's going to help you lose some confusion as far as what's happening between the function, its derivative, and second derivative. And that's what we're going to be working on some more as we go through the rest of these questions. All right, so for the next set of questions, we're going to look at a graph of a function's derivative, and then also its second derivative, and figure out what we can get from that graph. Okay, so in problem 2, I've given you a graph of a function. Here's f of x. And as far as questions go, let's lose these ones. There's actually no calc involved. If I ask for example, where is the extrema, I can just tell where that's at. Here's a minimum, here's a maximum. Okay, I don't need any calc concepts for that. Let's ask some different questions instead. Let's ask, for example, where is, let's say, f prime of x less than 0. Okay, where is my derivative less than 0? Well, that's going to be where my function is decreasing, where its slope is less than 0. So for that, we could say the interval from, we'll say 3 to -1. And then also looks like we're decreasing from 1 to 3. Same thing, asking the same question, but with getting derivatives involved, we're just putting more of a calc spin on it. All right, and there'll be more of what you see on the homework than asking these ones here. Let's do one more with the actual graph of f. Let's ask where is f double prime of x greater than 0? Now, a minute ago, we just said that when our function is concave up, the second derivative will be positive. Okay, so in this case, what we'll have is it looks like we are concave up through my graph until I get to 0. It appears that 0 is an inflection point where we're flipping concavity. And then it also looks like we're concave up from about 2 on the rest of the way. So those intervals we could say are -3 to 0 and 2 to 4. Okay, next up, let's look at the graph of a derivative. So let g be a differentiable function. So we have some function g. And below is the graph of g prime, the first derivative of g. So this graph here is not g, it's the derivative of g. And we want to use this graph, what we know about g prime, to identify the intervals of increasing, decreasing, extremas, concavity, and points of inflection for g. Okay, let's go ahead and do that. We'll start off with increasing. Okay, where's my function g increasing? That's going to be where my first derivative is positive. So this guy is going to be increasing with what we see in blue here. So we'll say from -6 to -2. Let's throw a union there to save some room. And where else this graph is positive, from 1, 2, 3, 4, 5, 6, 7 to 8. Oops. Eights are upside down or sideways infinities. Let's see if I can do that better. There we go. And then same idea, we'll say this graph is decreasing when my derivative is negative. So that's going to be what we see here in green. And now being a little picky here, it looks like my derivative is equal to 0 at x equals 2. So at x equals 2, we're going to say it's not actually increasing or decreasing. It's paused for a second. So depending on which calc book you're using, would be how you'd answer this question. Let's split this up into two separate intervals. Let's say it's decreasing from -2 to 2, doing nothing at 2, and then decreasing again from 2 to 7. All right, next up, let's talk about the relative extrema, the min or mins, depending on what we have, as well as maximums. Okay, now a function is going to take on a relative minimum when it goes from decreasing, turns the corner, comes up increasing. So in other words, where the derivative goes from negative to positive, that's going to happen here at x equals 7. And as far as a y value on that minimum, without knowing anything about the actual g of x, we can't figure that out. And by the same logic, we'll go have a maximum when our function goes from increasing to decreasing. So in other words, when the derivative goes from positive to negative, like it does here at x equals -2. Okay, now we do have that additional point here at x equals 2 where our derivative is equal to 0, but since it doesn't actually change signs here, it's not going to have a min or max. In this case, it's decreasing, pauses for a second with a horizontal asymptote, then just keeps decreasing. Okay, so not a minimum or a maximum. All right, let's get this cleared off so we can start talking about concavity and points of inflection. All right, so concavity, let's go with concave up first. And remember, we're not talking about where this graph we're looking at is concave up. We want to know where the original g is concave up. This is our derivative once again. Again, our relationship we looked at is we said that a graph is going to be concave up when its derivative is increasing. Okay, so as in we'll be concave up from, it looks like, -1 to 2. And then from, looks like we're going to hit the middle here. Let's call this 5.5. 5.5 through 8. Okay, because again, our function will be concave up when its derivative is, its first derivative is increasing. And then we'll be concave down when that first derivative is decreasing. So as in what we see in green here, from -6 to -1, and from 2 to that 5.5. All right, last thing then, inflection points. Those are going to occur where my original function, the g of x, changes concavity. Okay, so in other words, that's going to be where our derivative switches from increasing to decreasing. So we see that happening at x equals -1, at x equals 2, and also x equals 5.5. Okay, so in other words, the mins and maxes of our first derivative will be where those inflection points of our function happen. All right, next thing we're going to look at is a graph of a second derivative. So here, let h be a twice differentiable function. So we have some function h, And below we have the graph of h double prime, the second derivative of h. And we want to identify the concavity and points of inflection. Now notice I didn't include mins and maxes, increasing, decreasing on here, just because I can't get that information just from the double prime, just from the second derivative. We can find concavity. We can figure out where this function is concave up. All right, pretty straightforward. That's going to occur where our second derivative is positive. So as in from 1 to 4. We can also look at where it's concave down. That's going to happen when our second derivative is negative. Okay, first derivative is decreasing when that second derivative is negative. So we'll say here from 0 to 1. And from 4 to 6. And then finally our inflection points, that's going to be where our graph of the original function h switches concavity, changes concavity. And as far as our second derivative goes, that's just going to happen where it switches signs. So we know we're going to have a point of inflection at 1 and 4. Okay, so those will be the changes in concavity of that original h function. All right, final question for you then. Okay, identifying functions, derivatives, and second derivatives from 3 different graphs. Okay, so in other words, sorting them out. Here it says 3 graphs labeled 1, 2, and 3 are shown below. One's the graph of f, one's the graph of f prime, and one's the graph of f double prime. We want to identify each graph. Okay, so figure out of these 3 which one's the function, which one's the first derivative, and which one's the second derivative. Okay, doing this, there's a couple different ways we can think through it. I guess the first thing I'd be looking for is mins and maxes. Okay, notice that this graph 2 has a minimum right here, sorry, a maximum right here, and then it looks like a minimum right around here. And we know that when a function has a min or max, its derivative is going to be 0. So as far as determining which of these 2 graphs are the derivative of 2, what we'd be looking for are the one with zeros at that point. Okay, 1 has a 0 at this graph's maximum, but it doesn't have one at the minimum here. Okay, so what I know between 2 and 3 here is we could say that 3 is equal to the derivative d over dx of 2. All right, so 3 is graph 2's derivative, okay, based on those mins and maxes here. All right, the next question then is how does 1 fit into this? Is 1 the original function and then 2 is its derivative? Or is 1 give me the derivative of 3? Well, let's take a look. Now notice here there's no mins and maxes on 1, so we can't use the same logic. But 1's a pretty straightforward graph. It is increasing the entire time from left to right, meaning that its derivative has to be positive the whole time. Okay, now as far as between 2 and 3, 2 is the one that's positive the whole time, meaning that we could say that 2 is equal to the derivative of 1. Okay, so in other words, this case, our f would be graph 1, f prime would be graph 2, and then f double prime would be the third graph here. Okay, it kind of works out in a lame order, 1, 2, 3, but that's kind of the logical steps we can use to figure these out.